Okay, thanks for the invitation. And today I'll be discussing low degree dependencies for sparse random graphs. And so this is based on two papers. The first is joint work with Asaf Ferber, Matthew Kwan, and Ashwin Shah. And the second is with a very similar set of authors, Margalit Glasgow, Matthew Kwan, and Ashwin Shah. And the second is still forthcoming. So the focus of the talk will be, we'll be focused on singularity, on the singularity of the adjacency matrix of very sparse random models. So before going to sparse models, probably easier to, let's say, maybe think about the most canonical case, which is sort of the dense non-symmetric model. So let Mn be n by n random matrix. With Bernoulli 1/2 entries. So 0 with probability 1/2 and 1 with probability 1/2. So the question, sort of one of the natural questions that's been studied extensively is, when is Mn singular? And so the first and sort of maybe cheap answer to this, but sort of an important result, is Komlosh, which says, okay, it's a rare event. So even this is not obvious. So the probability that Mn is singular, this happens rarely. So but by now we have a much sharper understanding of this, in particular due to the work of Tikhomarov. We understand this relatively well. In particular, we understand the exponential rate of this probability. So the probability that Mn is singular is 2 to the minus n plus little o n, where the little o n is in the exponent. But this is not, while it gives you the exponential rate, it doesn't, there's an even stronger conjecture one can make, which is that the only dependencies asymptotically that contribute to the singularity probability are somehow very special. So in particular, the main conjecture is that it's 1 plus little 1 times the probability Mn has a left or right kernel vector which is say ei minus ej or ei. And maybe thinking in terms of kernel vectors is unnatural. All I'm saying here is Mn either has a row, which is a row or column, which is all zeros, or it has 2 rows, which are exactly the same. And you can encode this by saying you have a kernel vector of the above form. And so, at least conjecturally, the behavior is determined by these sort of very sparse and very simple dependencies. And in particular, this is what I mean by a low degree dependence, or sort of somehow it has a very simple combinatorial structure. And what I'll be focused on is sort of analogs of this result, or sort of settings where this is sort of the dominant phenomenon. And we'll be concerned about this when what happens with very sparse matrix models. And what I mean by very sparse, I mean discrete models with, say, order n entries. So there are two natural models here that have been studied. So the first is to consider, say, deregular graphs. So with d bigger than or equal to 3. So I just mean a graph G drawn from G and D. What I mean is just a graph on n vertices, a uniformly random graph on n vertices with where every degree is d. And it was a long-standing conjecture that was recently resolved by Huang and Mazaros independently. The dates are a bit misleading. These are publication dates. I think the papers are essentially simultaneous. The probability that the adjacency matrix of G is singular is little o1. And so this is all the long-standing question of Friese and Vu from the ICM. But at the level of what is this event, well, it happens rarely. But this is actually not the model I'll be concerned with. Sort of maybe the more natural model, if you're thinking about from the perspective of random graphs, and so notice the reason that, okay, one important thing here is note that in a deregular graph, the adjacency matrix never has a 0 row or column. So somehow there are none of these like obvious dependencies corresponding to having an all 0 row. And saying that the singularity happens rarely, sort of saying well, there are no obvious combinatorial dependencies, so there are no dependencies. The other natural matrix model that is the sparse is G and lambda over n, where lambda is a fixed constant. And here, well, the question I've been studying is actually not very interesting. So the probability that a G is singular, well, I mean, it's always singular. And this is not, it's not very interesting simply because G always has isolated vertices. And so just sort of for obvious combinatorial reasons, the matrix is not going to be non-singular. And so the first thing you should do is, well, okay, let's try to remove these obvious dependencies. So you could try to do is, let's say, remove, just remove all the isolated vertices. Is that graph is the adjacency matrix of that graph non-singular? And if you understand that, then you kind of understand the rank of the previous graph. Well, that's still an issue. You can actually have isolated trees, and these will give you dependencies. So let's say you just have an isolated cherry, or just any cherry. This kernel vector of -1, 0, +1 sort of shows you that you can't have any structure like this in the graph, where let's say these two vertices are not connected to anything else. So that gives you an example. Or, I mean, something else. Let's say you have an isolated 4-cycle, that also turns out to give you a low degree dependence. So if this were, say, isolated in the graph, the kernel vector corresponding to the numbers or non-singular, you need to do some pruning. And so, I mean, given that sort of all these structures are low degree structures, a natural thing to do is to core the graph. And the sort of, given that the structure here has minimum degree 2, the first place where you can really hope to create to really have a graph which is non-singular almost surely is the 3 core. So iteratively removing one gets the 3 core. And so now we can sort of ask the natural question, and this was a question asked by Vu, which is this graph non-singular? Is the adjacency matrix of the 3 core non-singular? And the first theorem I'll be mentioning is, this is the first work with Asaf Ferber, Matthew Kwan, Ashwin Sa, myself. So Vu's conjecture is true. So let lambda be greater than 0, be fixed, and G drawn from Gn lambda over n. Then the 3 core, then the probability of the 3 core of and so, as mentioned, this resolves the conjecture. And so, and I should note that there was work of D. Michel, Glasgow, and Moriera, which simultaneously did the statement with lambda tends to infinity, although the proof in the paper does also generalize to that setting. But notice that while the 3 core gives you a large subgraph, let's say for large lambda gives you a large subgraph that's non-singular, it doesn't exactly give you a characterization of the rank of the corresponding adjacency matrix. So while this is a subgraph where, let's say, you've maybe in a kind of just by removing these high minimum degree vertices, you sort of create a subgraph which is non-singular. It's maybe not the largest non-singular subgraph, and so it doesn't really give you an understanding. It doesn't, while it gives you a lower bound for the core rank, it doesn't exactly characterize it. And so for the next portion of the talk, I'll sort of be discussing maybe how you can get to that, and where that leads you to. So the first work in this direction. So I should notice that once P is bigger than roughly something like large constant times log n over n, it turns out the adjacency matrix is always non-singular. So this question sort of understanding the co-rank only becomes interesting when P is, let's say, small constant times log n over n. And the first work in this direction was due to Costello and Vu. So in the regime where P is, let's say, some constant times log n over n, Costello and Vu gave a characterization of the co-rank of A of G in terms of the largest set which does not expand. So in particular, you have that, what I mean by this is that the neighborhood of S is strictly smaller than S. And so this is natural. We'll actually see, so linear algebraically, this is natural because if you consider the set S, this corresponds to a size of S dimensional vector space. And sort of the image is always contained under AG within the neighborhood of S. So if the neighborhood of S is smaller than S, then, well, okay, this sort of tells you there's some linear dependence in terms of just the graph theoretic structure. But the result basically says that graph theoretic structure with high probability actually determines the corank. But for smaller p's, it turns out one needs to be slightly more careful, and there's a slightly more refined thing. But if you look at the statement, neighborhood of S being smaller than S, combinatorially, this has a very, it's very reminiscent of something, in particular of Hall. And where are everything I've discussed so far is somehow about adjacency matrices. Where are the matchings here? Is I think the question that naturally comes up. And what we're going to do, the next part of the talk, sort of trying to. There's a process that actually connects matchings and this rank problem in a very natural way. And it really follows from the following lemma, which is just a determinant computation, but it's a computation, so I'll show it. So what I've written here is a block matrix with the top block being 0, 1, 1, 0, and then the top row, the remainder of the top row being 0, and the remainder of the first column being 0. So graphically, what this corresponds to is you have some vertex of degree 1 connected to some other vertex 2, which is then connected to the rest of the graph, G. And the key point is that because you have that the determinant of this matrix equals the determinant of A, what this is telling you is that by removing 1 and 2, you change the rank. The rank changes by exactly 2. And so now you can try, so this now gives you a process. If you have a degree 1 vertex, if you have an isolated vertex, you can always remove it, and that has an obvious effect on the rank. But if you have a vertex of degree 1 connected to some other vertex, you can remove both the vertices, and that also has a predictable effect on the rank. But notice that this is very closely related to matchings, because if I was trying to find a matching in this graph, I could always assume that 1 is connected to 2 in the matching. And this observation is actually appears in work of Karp and Sipser. And this leads to what's called the Karp-Sipser core. So this process has a name. And what they were interested in was understanding the maximum matching in Gn lambda over n. So this is where ultimately the connection between matchings and this problem of rank comes in. And so this is just a computation. In particular, basically by using the formula for the determinant of a block matrix. The determinant we care about is the determinant of 0, 1, 1, 0 times the determinant of A minus 0 V transpose 0, 1, 1, 0 inverse 0 V. And if you just do this out, this is minus the determinant of A. And so this kind of very simple lemma leads you to this leads you to a natural process, which will give you control of the rank of Gn lambda over n exactly. So in particular, let me formally define this, the Karp-Sipser core. So iteratively remove of degree 0 or vertices of degree 1 and their neighbors. And this observation is not due to us. This is basically called what's known as the two-core bound on the rank. And I think this was observed by Almino and Saad, and Mazard and Montanari in the statistical. These are, I think, more statistical physics type papers. And so basically by this reduction, it suffices to understand the Karp-Sipser core. And our main result, so it turns out that this pruning is sufficient once lambda tends to infinity. So this is a result of de Michel, Glasgow, Moriera. It's from last year. So if you consider an Erdős Rényi graph where the average degree is tending to infinity, the Karp-Sipser core is non-singular with high probability. Unfortunately, when lambda doesn't tend to infinity, the statement becomes a little bit more complicated. And our main result is that outside of the obvious combinatorial dependencies, the Karp-Sipser core is non-singular. So let me put this theorem both in air quotes and in and explain what I mean by obvious. But sort of the punchline is if you can see the combinatorial dependence graph theoretically, then it exists, but those are the only ones. So for lambda not equal to e, the only kernel vectors and so obvious has to be explained. What they turn out to be is cycles of length 4, cycles where the length is a multiple of 4, and every alternate vertex has degree 2. And these are the only such kernel vectors. So let me just and this sort of generalizes the previous example I gave earlier, where you had an isolated 4 cycle. So in general, it's just these special cycles, and you can just count how many linear relations these small cycles give you. You count that, and with high probability, those are the only such linear dependencies. So hopefully the main result is clear. If there are any questions, it's actually a good time to take questions. Okay, if not, I guess I have like 20 minutes. And so our 20 or 25 minutes, I want to sort of maybe briefly discuss how these results are proved. I don't know if I'll be able to really discuss the differences between what happens maybe in the first work I mentioned regarding the 3-core and this more recent result that's forthcoming, but sort of I want to give a flavor of what maybe what's the general picture of the proof and the proof strategy at least. So the first thing is so our starting point is actually work of Costello, Tao, and Vu. And what they proved was the probability that a random plus minus 1 symmetric matrix is singular. This is little o1. Notice we're going to at least need to know how to do this because all the matrices we're considering are symmetric in this problem. By now, there are much stronger results. In particular, there was recent breakthrough work giving an exponential bound for this problem, but this was even this is not easy. And so the proof has the following structure. What you try to do is you sort of consider you consider building your symmetric matrix sort of by adding a row and column one at a time. And you consider how the co-rank of that matrix evolves over time. So this will be a proof sketch, and maybe we'll motivate what we do later. So let an over 4 be the top n over 4 by n over 4 block of the matrix, and define AT in the obvious way. RT will be the co-rank of AT, and what we'll have is that R n over 4 is less than n over 4. And furthermore, notice that this random walk takes bounded increments. Basically, because of linear algebraic reasons, you know that RT minus 1, well, this is at most 1. Okay. So the proof then proceeds by proving two things. So claim 1, if the co-rank of AT, if this is 0, and AT is unstructured, where I'm not going to be too precise what I mean by unstructured, then the co-rank at the next step is equal to 0 with high probability. So this is saying, well, okay, suppose I know my top block is already non-singular, then adding this random row, I stay that way with high probability. And claim 2 is that if the co-rank of AT is greater than 0 and AT is unstructured, then the co-rank of AT plus 1, well, it goes down with high probability. And this finishes basically because now you have a random walk which is drifting down. So in particular, let's consider a random walk. So we start at time n over 4, and we have to go to time n. And initially we start at some point an over 4, which is bounded by n over 4. And now almost every step, you know you're going down, And if you ever get to 0, you usually stay at 0. You might have the occasional up step, but you're usually going to trend down. And because you're trending down by 1 every time, and you have 3n over 4 steps, you're probably just going to be at 0 at the end of time. So modulo these two claims, the proof is finished. And so this general strategy of sort of looking at adding adding a row and column, and sort of seeing how that affects the co-rank, turns it into a problem of a random walk. And if you can show these two things, then you could prove the desired co-rank. Estimate. And so I'm gonna maybe the thing that's maybe less obvious. So claim 1 is more. These are both like really linear algebraic claims, and sort of what I mean by AT being unstructured sort of falls out of the proof. I'm going to omit the proof of claim 1 and sort of try to give an idea of the proof of claim 2, just to give you a flavor of what's happening. So, and for simplicity, you can just kind of do this for free, essentially. I'm just going to assume that the co-rank of AT is equal to 1. So what does this mean? So I have a T by T matrix, and since my co-rank is exactly 1, I know I have a T minus 1 by T minus 1 subblock, and because it's symmetric, I assume it's a principal subblock, which is full rank. And so now we're going to consider 2 steps. So first we have this bottom row VT. And we know that, VT originally can be written as, because it's not full rank, we know it can be written as, if the matrix were full rank, then if VT was in the span of the rest of the rows, was not in the span of the rest of the rows, you'd be full rank. So VT has to be in the span of the remaining rows. So you know that VT can be written as Li times Vi for I equals 1 to T minus 1. But now when we go to the next matrix, what do? We add a random set of signs, in particular epsilon1 to epsilon t. And now if you consider sort of what has to happen for this relation, for this linear relation between VT and the remaining rows to continue. For it to continue, what you would need is, say, epsilon t to equal the sum from I equals 1 to T minus 1, Li epsilon I with high probability. You need this to happen. But this doesn't happen with high probability if there are many non-zero. If there are many non-zero Li. And this turns out not to be so hard to establish. This is saying that the original matrix doesn't have a kernel vector, which is sparse. And you can also then sort of so this increases the rank by 1, and now you can also check that that when you add this bottom epsilon 1 to epsilon t, which corresponds to adding the bottom row, you can also check that this will you get the same condition. You get the same condition for it not being in the span of the remaining, like basically the new column you add for it not being in the span of the remaining columns. And so the co-rank increases twice. The rank increases twice. I'm being a little bit informal, but yeah, okay. It's linear algebra and it can be done. And so this kind of you went from, so since your original co-rank was 1, and your rank increased twice, notice that the dimension of the matrix went up by 1. And so this means that your co-rank is now 0 with high probability. And so that finishes the proof. So all we need for this proof to go through really is that you can show, so this proof relies on two key things. First, that when you add this row and column, somehow they're independent from what you've seen before. And that, so that's the first observation. And the second is that you need these sort of subblocks to have good unstructuredness properties. Where unstructuredness in this case means that you don't have a kernel vector which is very short. And given that, you can hope to run an argument like this. That plus some sort of trivial estimate on the original co-rank. And the strategy we have is roughly follow this, but sort of each of the three steps I mentioned breaks if you sort of consider it naively. So, well, okay. So the first thing is, notice that when we considered the sum of Li epsilon I from I equals 1 to t minus 1 equals epsilon t, we say this happened, they're not equal with high probability because Li has large support, and epsilon I are plus minus 1. But if you consider Gn lambda over n, there's really not nearly as much randomness. So ignoring the fact, let's consider sort of doing this process. We know we're not going to do it in Gn lambda over n. We're going to do it eventually in the Karp-Sipser court, but let's consider Gn lambda over n. Gn lambda over n, every vertex has roughly degree that's order constant. So if only a constant number of epsilon I are non-zero, one can't hope for such a guarantee. And so this is problematic, right? Because most vertices in Gn lambda over n are, let's say, constant degree. So you need to, these sort of steps you add back have to be special in some way. And so what we do is instead of just taking sort of adding back in random vertices, you have to add back in sort of special vertices. And so the key idea is to say remove high degree vertices. So consider, so Rn, this is now going to, let's say, be the, we're going to consider, let's say, the three, let G be the 3 core of some. We're going to let G be the 3 core of Gn lambda over n. And what we're going to do is, in order to get around this problem of sort of the vertices you're considering this process being, let's say, very low degree, I'm only going to remove high degree vertices. So remove the vertices, the beta n vertices of highest degree. So there's a slight lie here, which I will get to, but okay. So now what do we have? We have some matrix where I'm going to call it Rn minus beta n, and then I have beta n vertices I'm going to add back. So now, in order to possibly start this strategy, we need some bound on the co-rank of Rn minus beta n. And we can't take the trivial bound like before, because if you want these beta n vertices to have a high degree, you want to send beta to 0 slowly. So you need some bound, and here there's actually an extremely powerful tool of Bordenave, Lelarge, and Salez, based on sort of this is based on using sort of the fact that if you define this matrix correctly, it converges in Benjamini-Schramm to some limit, and that lets you read off the rank up to little o(n) factors. You can show that, let's say, the rank of Rn minus beta n is less than beta n over 2 with high probability. So now, okay, we have this matrix. We know, or sorry, not that it's rank, its co-rank is small. Forgive me. And so now, okay, now we just need to show that adding back in these vertices, you have this process that the co-rank goes down. Now there are some issues because, well, what does it mean to add back in this vertex? You need to understand some really weird, naively, it seems like you need to understand some very weird conditional distribution. In particular, that what does it mean to remove, to take the highest degree, like what is the conditional distribution of the neighborhood of one of these vertices into the remaining parts? And here you need to find, basically the key issue is, what is the remaining randomness? And so the key fact that sort of saves the day is that, or that lets you sort of get started, is the 3 core is equidistributed over all graphs with minimum degree 3 conditional on the number of edges and vertices. So there's some randomness here. And what you do precisely is you remove beta n vertices of highest degree from the last alpha n vertices. And if you define the set, call the set S, this is the set of removed vertices. If you define it carefully in this way, what you can show is that, okay, so I have the set S of beta n vertices, and I have the remaining graph. There's this set of alpha n minus beta n. So I had this original set of alpha n vertices. I extracted the beta n highest degrees. The conditional distribution from this vertex to this set is kind of hard to understand. Furthermore, when you extract these vertices in S of high degree, some of these vertices now have degree less than or equal to 2. And that's problematic because if you think about it, you know the final graph has degree higher than 3. So you know one of these vertices has to connect to it. So the conditional distribution there is kind of also not so clear. But what you can show is, okay, given the number of edges from this vertex to the remainder, it's sort of uniformly random. And so this gives us access. The fact that from each vertex through some very large portion of the graph is sort of the neighborhood is uniformly random. This gives us access to uniform, sort of uniform randomness. And one can then hope, and one therefore just needs to prove unstructuredness guarantees. And okay, so now we're kind of in position where you can, let's say, hope to apply more sort of hope to use this idea. So this fact here, I mean, this is the fact here that with high probability this is non-zero. This is basically Erdős Littlewood offered, and you can hope to use these style of techniques to now sort of show that the rank goes up, modulo that you prove these unstructuredness guarantees. And so now this is a delicate thing, because these models you have, these sort of conditional models on graphs you have, they're not, I've defined it in some way, there's some amount of randomness left, but it's not a particularly easy model to work with. And it turns out if you set this up correctly with a bit more fiddling, what you can do is for the 3 core, or let's say, for the 3 core, properties coming from the fact the 3 core is just minimum degree 3 subgraph of Gn lambda over n. Are sufficient. But for so I don't really want to go into too much details, but okay, you can kind of just sort of by thinking about high degree subgraphs of Gn lambda over n and doing enough union bounds, you can prove these sort of properties. For the Karp-Sipser core, it's core, one needs to be much more delicate. In a more delicate manner. And maybe just a hint that the sketch is sort of maybe a bit misleading is, I told you for the Karp-Sipser core, if everything I said were true for the Karp-Sipser core in the same way, the Karp-Sipser core would be non-singular with high probability. But these subgraphs that I drew, they occur with Poisson probability. And you do need your argument to at some point see these subgraphs. And this comes in sort of in the delicate nature of sort of tracking what exactly do you need for this unstructuredness. In particular, what you roughly at a high level prove is that these are the, you either are coming from one of these combinatorial type dependencies or any other sort of linear relations very unstructured. This requires quite a lot of work to make precise, but that's sort of what's happening in this random walk process. And with that, that's actually all I wanted to say. So thank you once again, and yeah.
All right, thank you very much for that talk. Do we have any questions? That does not seem to be the case, so thanks again.